Hello class, welcome to this week's lecture on neural networks. We'll be looking into detail on what a neural network is and how does it work before moving into the second lecture for this week, which will be about the different types of neural networks you may encounter. Neural networks for speech, for language, time series, images, etc. First of all, why do we use a neural network? We basically use a neural network when we cannot draw a linear line to separate our two classes. Okay, so in the case of this image on the left here, we have purple dots and red dots, and we can't just draw an image to separate them. Instead, if we use a neural network, this allows us to come up with any polynomial function that might separate these classes. In this case, it might be a circle. So this gives us the flexibility to deal with very different type of data. Neural networks, actually, as you saw in the lab from last week, problems like XOR, very simple problem, right? You have 4 inputs and there's only 1 or 2 possible outputs. Still, we cannot separate it with a linear line. Our logistic regression model did not work for this problem. Okay. So we need a more complex polynomial function. So this week, from the lab or the homework, I forget, we'll see if we can use a neural network to solve this super simple problem. Okay. Now, neural networks are typically depicted or drawn like the figure on the right. What does all this mean? We have different layers in a neural network. That would be the vertical columns. If you have more than one layer other than your input and output layer, so you have your input layer and your output layer, then we call this model a deep neural network. So deep neural networks have many layers in between. Each layer consists of nodes, which are just the little dots in the center. And we'll have a look at how the output value of each node here, everywhere, is calculated simply as a linear combination of all its inputs combined with weights. Okay. So for instance, this X here will consist of a linear combination of all 4 of these inputs. Okay. Right. Oh, we have a nice animation here of how a training barrier evolves during training and can be made nonlinear. Okay, so each set of neurons, so each neuron, which is a ball in the previous figure, each neuron's output is formed as a linear combination of all its input. Okay, then this linear combination is put through an activation function G to form the actual output of the node. Okay. What does this mean? When we calculate the input value of the node, we have a linear combination of all the x's with a vector of all the weights, plus a bias term. Okay, the bias term just shifts the result. Then we'll calculate an activation function of z, z, to calculate the final output y hat, it's predicted y. Okay. Now, interestingly, this whole perceptron model was first invented or intended to be a mechanical hardware. So it wasn't really software. It was built as hardware. It was called the Mark I machine, and it was actually used for image recognition tasks by the US Navy. I have a little video here to show you the very first perceptron built as a hardware. How do we play that?
In the 1950s and 60s, scientists built a few working perceptrons, as these artificial brains were called.
He's using it to explore the mysterious problem of how the brain learns.
This perceptron is being trained to recognize the difference between males and females. It is something that all of us can do easily, but few of us can explain how. To get a computer to do this would involve working out many complex rules about faces and writing a computer program. But this Perceptron was simply given lots and lots of examples, including some with unusual hairstyles.
But when it comes to a beetle, the computer looks at facial features and hair outline and takes longer to learn what it's told by Dr. Taylor. Andrew Cruikshank's wig also causes a little heart-searching.
After training on lots of examples, it's given new faces it has never seen and is able to successfully distinguish male from female. It has learned. While promising, this approach to machine intelligence virtually died out.
Okay, do you notice how they say that this technology has died out? Definitely because of the AI winter. And I can tell you that using image recognition for using neural networks is very much popular today, as you all know. So I've already very briefly showed you how the Perceptron works. Let's go over it again. So we see that we have a node. The node is here split into two elements. We have these two are actually the node. We have first a linear combination of all the inputs. Typically also has a bias, but sometimes we omit this for brevity. And an activation function. In the case of logistic regression, in fact, this is basically one perceptron. Okay. Remember, logistic regression first does a linear combination of the inputs, and then it feeds it through a sigmoid function. Okay. Basically, one perceptron. Okay. The activation function is what makes these linear combinations non-linear. Okay, so they would allow your network to learn these complex shapes. I mentioned that usually we add a bias to the model. So here, bias will also have a weight. Okay, it just shifts our model. Now, if we rewrite this a little bit, so using linear algebra, we can actually replace the whole summation over all the different weights and replace it by a vector W. The vector W will be a vector of all the weights. The vector X will be a vector of all the inputs. And we note that we need to transpose X so that we can take the dot product of both. All right, so activation functions. Once we have this linear input, we apply an activation function G to our linear combination. In this case, let's take an example and we look at the sigmoid activation function. So sigmoid takes any real number and transforms it into a scalar output between 0 and 1. So it's a very bounded output, ideal if we're predicting probabilities. I've added a little plot here as well, so you can see the sigmoid function, but we talked about this one in detail in the last class. Okay, but there's a number of other activation functions that we could use. I put a few common ones here, but there's a bunch. I added a link to the Pytorch documentation where you can actually find an enumeration of all possible activation functions. Okay, sigmoid, we talked about this just now. You can easily call this in Pytorch using the command torch sigmoid. We could have a simple threshold function that basically cuts the output of our linear combination of input variables using everything that's bigger than 0 will be 1, everything smaller than 0 will be 0. Another popular one is ReLU. You can call that one using torch ReLU. And ReLU basically deletes everything, or puts to 0 everything that's smaller than 0 and makes the rest a nice linear line. Okay. There are different types of ReLU, which will come back later in this class as well. Okay. Now, when do we use certain activation functions? Okay. If we use if we're working on a regression problem, we typically want our output to be between minus and plus infinity, okay? Because we want to predict an actual number. So then we need to make sure that we use a linear activation function or something like ReLU, which allows for a wide range of outputs. When we're training our network, just like in logistic regression, we need a loss function. The loss function is the thing that we'll try to minimize when we're training our model. Actually, what does training a model mean with neural networks? We want to find the optimal weights. Okay? So the weights is what we need to adapt. Our loss will guide us in that process. Now, if we're doing regression, we can use a simple mean squared error loss, for instance. The mean square error loss, I'm sure you remember from last class, it just basically takes sort of the distance, the mean squared distance between the predicted output of the final node in the network and the actual labels. Other problems include binary classification. We talked about this at length last class. For binary classification, sigmoid is a very popular activation function which gives us basically confidence or probability. It outputs a value between 0 and 1. When we're optimizing a neural network for binary classification, we can use binary cross-entropy loss, again, which we derived during last class. Now we have multiple categories, not just binary categories. We can use something called softmax. I mentioned the softmax equation as well during last class, and basically we'll output 0 to 1 for each of the classes, and the total sum of all probabilities would be 1. Okay. So how does this look like? Imagine for softmax we have 3 possible classes, class A, B, and C, and we might, our softmax layer might output 0.1 for class A, 0.3 for B, and that means, by definition, that C needs to be 0.6. In this case as well, that means you're predicting that your input is part of class C. To optimize a categorical neural network, a neural network that does multi-class classification, basically, we use something called cross-entropy loss. When we're doing something called multi-label classification, that means we can have more than one output label for each example. In this case, we use softmax for each class, still with the total sum to be 1, but for our loss function, we can use binary cross-entropy loss for every class. Okay, so activation functions are very important because they are the ones that will allow us to learn very complex class separation borders, very polynomial. They introduce the nonlinearities into the network. So again, going from linear separation to polynomial separation. Okay, now let's take an example of a perceptron. What if we have a perceptron with the following weights? We have the bias weight 0 is 1, and we have W being 3 and minus 1. Okay, it's marked both in the equation here as well as here. Okay, so the weights are often put on the arrows. Now we can feed this into our linear regression model. If we fill this in here, then we can calculate the equation of the linear regression, which basically just is a line which we can show in a 2D graph. We can do it in a 2D graph because we have 2 input variables here. So it quickly outgrows 2D in real life. Remember, we still will be applying G, the activation function, later on. Okay. So in this example, we can draw the calculated linear line in this plot. Okay, simply by equating the output of the line, by equating this part to be 0. So assume we have a new input that we feed the network and we want to know the prediction. If we have an input x that is minus 1 and 2, that means that we can fill this in the equation. We just plug it in and we calculate that it is minus 6. Okay, so here is again the point if we add it to our 2D graph. Now, if we apply the sigmoid function to it, we actually get 0.002, so we get our probability. So let's look at this graph in more detail. We have our linear separation line, and we have z, which is basically our linear regression. Z bigger than 0 or smaller than 0 defines our class boundaries here, and it is mapped to y using the activation function g. So in this case, the activation function would transform 0 to 0.5. So if you fill in 0 in the sigmoid function, you get 0.5. So if we build a neural network with perceptrons, how does that look? Now, we looked at this equation already. So we have the linear combination plus the bias of all the inputs plus the bias. And we can combine multiple of these perceptrons together. Okay. If you combine multiple ones into what we call a layer, you can write this in Pytorch as torch NN, neural network, linear. Okay. And a layer like this is typically defined by the number of input features, in this case 3, or M, sorry, the number of output features, 2, and the bias, if there's a bias. Bias is here, so we have it as true. All right, so that means that instead of just calculating this equation once, we need to do it for every node in our layer. So typically we have many of these nodes in our neural network. That means for each hidden layer node, we can write it as going from 1 to m, the number of inputs here. Summarize overall the inputs, the linear combination. And for the final output layer, for each of these nodes, we take the sum of these z's we just calculated here. And we summarize these over the number of hidden nodes. Okay. Now, when we design an architecture, as we call it, it's sort of an art. Okay. We need to design our loss. We need to design the algorithms we use to optimize the loss. How do we represent our data? Do we augment the data? How many layers do we use? How many nodes are there in each layer? All these hyperparameters, they influence the performance of our network very strongly. So whenever, for instance, you're doing a research paper on neural networks, it's important to not just say, this is our architecture. In fact, you want to test the architecture, maybe try a few different combinations, an exhaustive search of all these combinations, and report results for different configurations. Okay. All right. Now let's take a detailed look at this example. If we have, if we're calculating this for Z2, that means we take a linear combination of all the inputs, x1, x2, up until xm, which is represented here. We add the bias to it as well, which we can write as a simple linear combination, okay, from which, of course, the activation function will be taken. Now, we can expand this perceptron model to a deep neural network. What does that mean? Basically, we have many, many layers. Okay. The number of layers is the depth of the network. Okay, for each of the layers, there's an example calculation for a layer K. For each of these layers, you use the same formula to calculate the sum of all the previous inputs, after being fed through the activation layer, summarized over the number of nodes and k. Okay. In Pytorch, how does this work? It's pretty easy to define a neural network in Pytorch. For instance, here we have a 4-layered network. I'll go over the code first. First of all, we have some import definitions, as we always do. Whenever we have a neural network, we first define it as a class. Here I call it net, but you can of course name it as you want. Net is an instance of neural network module, so that's important. It always starts with an init function in which you define what type of layers you're going to be using. In this case, I'm going to be defining 3 fully connected layers. Fully connected layers are the types of layers we just saw. That means each node is connected to all of the nodes of the previous layer, fully connected. And each fully connected layer is what we call in Pytorch a linear layer. It has a certain input and an output. Okay. Notice that the output of the previous layer needs to match the input of the next layer. So if this were to be, I don't know, 20, this also needed to be 20. Okay. The final output here is 10. Now, by defining FC1, FC2, and FC3 doesn't mean I'm actually building the network yet. The building of the network happens in the forward layer. Okay, sorry, the forward function. So in the forward function, I call a first layer with ReLU activation. So the actual sequential definition of the layer needs to happen in the forward function. Now here I have an input X, which I get here. From X, I send it to the fully connected layer 1. Then I give it a ReLU activation. And I say, replace X with this. Then that same X is fed to fully connected layer 2 with ReLU activation again. And again, I call it X. And this continues, same thing through fully connected layer 3, except now I do softmax activation. Okay. So if you print net, then you actually will get a definition, just a few lines on what is being done in your neural network, so that can be a nice check for you. In the lab, we'll be looking at some of these things. Okay. So here's an example. Let's go through the calculation. Okay. Let's take a simple neural network with 2 features. Will I pass this class? It depends on the number of lectures you attend. It's not really the same. Let's say the number of video lectures you watch, and next to the number of hours spent on the final project. So we could represent all this in terms of these 2 variables. The green dots are the previous examples we've seen last year where people pass green or fail red. And now we have a new student that is a purple one here, and we're wondering, do they pass or not? Now that means if we feed our example data into the network, so we have a value for x1 and x2, we will get a prediction y hat, and we can compare this predicted value with the actual value. Okay. In this case, it doesn't seem very good because our predicted value is 0.1, whereby we want to predict 1 that it will pass. Okay. Now we can use the loss of our network to measure the cost from mispredictions. Okay. So L is a function that measures the loss based on the model weights and the actual values. Okay, so we call this function L, the loss, that takes as input the predicted values, compares them with the actual labels, and the predicted values are based on the current weights of the network. So that's good for one example. So we are looking at one student, 4 and 5. But typically, you measure your loss over an entire data set, more specifically the test data set, or sometimes a bridge data set, as we've seen. Now, in this case, our data set would consist of the previous student that we mentioned, but also a bunch of other students. Now, if we feed all these inputs through the network, we get a set of outputs, f, x. And for each of these outputs, we see, do they match? Yes or no? Okay. So basically, what we do when we calculate the total loss, J of W, so J given the weights of this network, we take the loss between the predicted and actual value and we average it over the data set. The data set here consists of n entries. Okay. So this J of W is known as the objective function, cost function, etc. Okay. Now, in the case that we use a binary cross-entropy loss, okay, something we discussed last week, we can actually calculate JW as follows. Okay. In Pytorch, it's very easy. You just say use BCE loss. Easier than doing the actual calculation, right? But if you take your slides from last week, you see that this corresponds to the formula of binary cross-entropy loss, where we take the actual values and we multiply them with the logarithm of the predicted values. We take 1 minus the actual value here, and we multiply it by the logarithm of 1 minus the predicted value here. Okay. So this again gives us binary cross-entropy loss, and cross-entropy, as you remember, is something, think of physics as well, surprise, something sort of the amount of chaos in your network. Okay. So we want to minimize J of W. Okay. If you're doing classification, that works. If we're doing regression, then we actually output continuous real numbers. So here our fx works a little bit different. In this case, we're predicting the actual grades and not if they'll pass or not. So in the previous slide, we had a probability of how likely it was that they passed. Here we have a continuous real number of the grades, meaning that our loss function JW actually also needs to change. We use mean squared error loss, for instance. There's other option. In Pytorch, again, very easily done. If you define the loss criterion, you just call MSE loss. And again, actually, if we would write this out full, the formula is a little bit shorter. You just take the difference between the actual and the predicted value, and you take sort of the Euclidean distance between them. Okay, and you average it again over the data set n, because there are n elements here. All right. So how do we train the models to optimize the loss functions? So we want to find the weights that achieve the lowest loss as we defined by our function JW earlier. So J, the loss of the network, the total loss of the network, given weights W. Okay. So when we do our loss optimization, we get into the domain of optimization, which is quite complex. But what we basically want to do is, suppose we visualize all possible values, combinations of weights, together with their resulting loss function. We could imagine an area or a landscape whereby the red spots would be the high value for the loss function. And what we want to do is we want to slowly move and find not a local optimum here, because we'd get stuck. We want to find the very best minimum, which is the global minimum. Now we can use functions like gradient descent to slowly make small changes in the weights until our loss function is minimized. Gradient descent is sort of the most basic algorithm. We'll see a few other options in a second, but let's start with gradient descent. Gradient descent, we start by initializing the weights randomly from a normal distribution. Then we loop the following until it converges to the best minimum. First, we compute the gradient. Remember that from last class? Gradient descent. So first we start by initializing the weights of our network randomly. There's some other strategies for initializing the weights, but gradient descent, we start from random. Then we loop the following until convergence to the global optimum. First, we compute the gradients, or the partial derivatives of the function jw given a change in weight w. And then we update the weights using the following formula. Okay. We calculate the gradient here. We multiply it by the learning rate mu here. And we subtract this whole term from the current weight to get the new weight. Okay. In Pytorch, it's done pretty easily. We just select the optimizer as being gradient descent. Then you feed it the model parameters, or the w's, which is what it needs to optimize, and you give it the learning rate LR. Okay. So during the model training itself, what you do is you loop over all the items in the data set, whereby you have x's and y's, and you start by by zeroing the gradients. Remove the gradients, put them all to 0. Then you do a feed forward pass through the model. That means you feed the model your input and you get the predicted outputs. Okay. Then in the loss function, whichever loss you defined, I left it open here, you feed the target labels the predicted outputs y hat and the target labels y. Okay. Then we do a backward pass to calculate the gradients, and then we actually change the weights. Okay. This is gradient descent. So how do we compute these gradients? So gradients are an interesting feature of Pytorch. It's one of the reasons that all of these tools are so fast, because we are able to use something like gradient descent instead of calculating the full change of the final output function given a change in weights. We only need to calculate the change in weight, which basically is the strength of neural networks. So how does it work? In the case here that there's a change in weight 2 in our network, okay, here, we need to calculate the effect of JW given that change of W2. Okay. We can split that up in a multiplication of 2 terms. First, it would be the change in WY given a change in the predicted Y. Okay. Then we multiply that with what is the partial, so the predicted change in Y hat given a change in W1. Okay. So this is if we're calculating the predicted change in JW given a change in W1. So this is something called the chain rule. It means we can sort of split gradients or partial derivatives into a multiplication of their individual parts. Okay, so then if we're still calculating the change in JW given a change in W1. So we first, as we said before, we calculate the change in JW given a change in Y hat. Then we multiply that by a change in Y hat given a change in Z1. So again, we use this chain rule. And then we calculate a change in Z1 given a change in weight 1. So you get the idea here. You're calculating the gradient of each step of the calculation that happens between between W1. It's fed first into linear equations to calculate Z1, activation function, another linear equation, etc., etc. So using the chain rule, we just break it down into each individual operation. Okay. Let's look at a very detailed example here. Okay. So imagine you have a single training set. It's been given inputs 0.05 and 0.10, and we want the neural network to output 0.01 and 0.99. Okay. So the inputs here and the outputs here, the desired outputs. So how do we get started on this? So first we do a forward pass through the network. We just calculate what the predicted outputs are before we make any changes to the network. So for the hidden layer node H1, okay, we can start by taking the linear combination of W1 times the input I1, okay, here. Then we see that it gets an input from I2 as well, with weight W2. So we take the linear combination of this plus the bias, because there's also a bias in this network, which goes to H1. Okay. If we calculate all this, we get 0.377, which would be the value at H1. 5, sorry. And then in H1 there's an activation function. In this case there's a sigmoid activation, so we plug this in here to get the actual output of H1 after activation, 0.59. So then we do the exact same thing for H2. And you can calculate to see if you get the same results. Now we're going to repeat this for all of the output layers using the hidden layer as input. So we start with output, the output layer node O1. And this is basically a linear combination of W5, W6, and the bias B2. Okay, so again, all of this is plugged into the linear regression here. Let's say linear combination of input from all the previous hidden layers. If we calculate this based on our inputs, these are the H1 and H2 that we calculated in the previous slide, then we get the output 1.1 for the output layer. Again, we have a sigmoid activation. Plug that result in here, and we get the actual output after activation to be 0.75. Okay. Same can be done for O2. All right, so that's the forward pass. That's the easy part. In this case, we're using a mean squared error, so we can calculate the total error. Now remember, on the first slide of this example, we saw that the actual desired or the target label for O1 is 0.01 and 0.99 for O2. So mean squared error means you do the predicted value minus the actual value, and you square it and you take the average. Okay, so if we do that, plug in the target variable minus the predicted one that we got from the previous slide, we get 0.27 to be the loss resulting from O1. We also have a loss resulting from O2, so we can do the exact same thing from output node 2. Okay, now note that maybe it might be more intuitive for you to look at the total loss as sum of 1 until 2 of these error terms. It would mean like y minus y hat square. But we sort of already put the 1/2 inside the term. So this would be what we're calculating at each part here and here. Then we just need to add them up. So the 1/2 and the sum was already included here. Okay, just to make that clear. All right, the next step. We're doing our backward pass now. So first we did the forward pass, then we calculated the mean squared error. Now we're going towards the backward pass. And our goal will be here so we can calculate the gradient so we can change the weights. Okay. First, let's see how much should we change weight W5. W5, where is it? It is here, the weight of the last layer. How much will a change in W5 affect the total error? So that means we're going to be calculating this partial. This partial, we can use the chain rule and split it into 3 elements. Okay. the change in the total error given the final output layer O1, the final output layer given a change of the network output of O1, and then a change in the network output O1 given W5, a change in W5. Okay. All right, so notice here there's a small difference between the network output here and the output. What happens here is a sigmoid activation. Okay. So WNet is the output of the linear combination, and the output is a sigmoid after the sigmoid activation. Okay. So now for each of the terms in the following equation. So how much does the total error change with respect to the output? Well, first of all here, let's look back and remember our error function, mean squared error. We're going to be using that to calculate the change of the error based on it with regards to a change in the output O1 here. Remember from our previous slide that using the chain rule, we can split up our change in total error into 3 terms. So first, we're going to be looking at the first term here. So if we take the derivative of this first line, and we get the second line. Okay. How do we get from A to B, you might ask? Here's a little math refresher. If we take the partial derivative for a function x minus y squared, partial derivative for y, for change in y, then we get 2y minus 2x. Okay. Now, this is not a math class, so we're not going to go into details why. If you're interested in getting partial derivatives, there's a great website. I think I linked it to in the homework, Wolfram Math, which you can input any function, it'll give you the partial derivatives. So let's have a look. Here we have x minus y to the power of 2 and we take the partial derivative for y. Okay, so then we get x minus y to no power and times 2. So that's almost the same as we see here, except we see y minus x instead of x minus y. So that is easily adjusted by adding the minus 1 here in the multiplication. All right, so this is the partial derivative for the total error towards O1. So if we fill in our values that we calculated before, so target O1, we want the label to be 0.01, and our predicted label is 0.75. So here we get the first partial derivative. Okay. So remember also that this term sort of totally nullifies when we take the partial derivative. If we take the partial, it becomes 0. Why is that? Because there's no mention of out O1. So meaning the partial derivative of a constant is 0. Okay. All right, so the next step in our equation, this one. Remember this one, we're moving on here now. The next step is the sigmoid activation. So now we need to take the partial derivative of the sigmoid derivation, and I added a little math refresher here again. Now, to get from the partial derivative to this is actually very complicated. So instead of giving you 3 slides of math, I can refer the interested parties to this website, which is a very nice article that explains all the steps of the derivation and the calculation. But suffice it to say that the partial derivative of the sigmoid function is out O1 times 1 minus out O1. All right. So we can fill this in, again, the calculated predicted value times 1 minus the predicted value, and we get our next derivative. So how much does the total net input of O1 change with respect to W5? So a change in weight 5. This brings us to our last term we need for the partial derivative calculation, for the gradient calculation. And first we need to realize that the network output is a linear combination of weights 5, weight 6, and a bias. So we're calculating O1 here, the network output. It has an incoming value for W5, W6, and the bias. Okay, so it's just a linear equation here. If we take the partial derivative for Y5, it's very easy here. First of all, these terms become 0 because they're just constants and they don't contain a variable Y5, W5, sorry, Dutch for W. And then here we have W5 times out H1. Taking the partial derivative of that just becomes W5 times out H1. W5, sorry, to the power of 1 minus 1 equals 1 times the constant here. Meaning this is just out H1, which we had calculated before. Okay. Now, to get the final partial derivative, remember here, we need to multiply these three elements to get the final value. All right, so here's the formula again. Multiplying these three elements that we calculated gives us the total partial of the total error given a change in W5. Okay. Now let's get to the gradient descent equation. Finally, we know that the new weights are going to be the old weights minus the learning rate. Learning rate is just a constant that we set. Usually it's like 0.001, 0.01, but that's a different story that we'll get to in a minute. Times the partial that we calculated here, right? And this gives us our new weight, H5. So W5 will be updated to new weight. That's it. That's one step of backpropagation for one weight. Now we do the same thing for each of the weights in the network. Noting actually that to calculate a change in weight W6, W7, we still use the original value of W5. So we don't change the weight yet until we do the backpropagation for the entire network. Okay. All right. So let's move on. We've done all the weights here and here, but now let's move back to before the hidden layer or the hidden layer, and we calculate the partial for a change in weight 1. Okay. Now weight in weight 1 is a change in the error given the output of the hidden layer times a change in the hidden layer given the network output here, and a change in the network output given finally a change in W1. So using chain rule again, we get all these individual elements, and as you'll see, this will actually be further split up. So it's a very similar process, but we have to take into account that now the changes of weights, that the chain is longer basically, right? So the output of each hidden layer neuron contributes to the output and thus also the error that we're calculating of multiple neurons. Okay. All right, so if we take a look at the total error given a change in W1, I think we're still calculating W1, it's not going to only influence our output node 1 like we had in our previous example. This change in weight 1 also propagates like this, and it'll influence our output node 2. Okay, so we need to calculate both of these, meaning that we need to look at both partial derivatives summarized, because the total error is the error resulting from node 1 and node 2 in the last layer. Okay. Let's start with that first term, and the first term focuses on output layer O1. It can again just be split like we did earlier. It is network output here, partial of this times the partial of the network output given a change in H1. So we calculate this using the values that we actually obtained earlier. So our change in network for output for O1 is given a change in the output of hidden layer 1, node 1, would be equal to W5. Why is that? So our network output can be written in this equation. Again, it's just a linear combination of the weights, these weights. Oh, sorry, these weights only, excuse me. And if we take the partial derivative towards H01, again, this term drops, then this becomes 1, and this is a constant, so it stays, so that means it's W5. The value for W5 is 40 here, which I removed for you, occluded for you. So 0.5 is this partial derivative. Okay, are you still with me? I know it's a lot of math, but it's quite, hopefully you'll see that it's always the same repeating process. You go through each step of the forward function, and for each function you take the partial derivative, you fill in the values. Okay. So again, we can plug in everything to get the change in error giving the change in the output layer H1 here. Same procedure for the second output node. So then, therefore, the total error is the sum of these two error terms, 1 and 2, and it boils down to this. Okay. So now that we know how the error responds to a change in the hidden layer 1, then we can actually go one step further down the network. And the first thing that we encounter there is a sigmoid layer. Right? Because first you do linear regression, then you obtain the sigmoid activation function, but we're going backwards here. So we first encounter the sigmoid activation function, for which we know now it's a very complicated derivative procedure, but it ends in the output of hidden layer 1, node 1, times 1 minus out H2, H1. So we fill that in, we get again our derivative. Now, the next step back is first we had the sigmoid. Now we have again the linear combination of weight 1 and weight 3. They all arrive in H1 and the bias 1. So this equation forms the network output in H1. Okay. So let's take the partial derivative for a change in W1. That means this is a constant, so it drops to 0 if we take the partial derivative. This is W1, is the partial derivative of x is 1, meaning that this becomes 1, and this considered a constant in the multiplication, meaning I1 is all that's left if we take the partial derivative. We fill that in. Again, I totally remove, oh no, here it is. I1 is 0.05. Okay, so putting that all together, using our chain rule, we multiply all of the terms and we get the final partial for a change in the error given a change in W1. And that's it. Okay, we can use this again in the formula for, this is a term we just calculated, the formula for gradient descent times the learning rate. The learning rate here is 0.5. Very often you'll see it's like 0.01 or quite small. And we have the old weight minus this term that we just calculate forms the new weight. Okay, and we update the network weights all in a similar fashion. Okay, easy, right? All right, so finally we've updated all of the weights. When we feed forward the 0.01 and 0.1 outputs, originally the error in the network was 0.29, etc. We calculated this. After a first round of backpropagation, if you were to change all the weights to the new weights with the plus sign that we calculate, you'll find this error, which is slightly less, as you see. Okay. Now, it might not seem much, but when you repeat this process 10,000 times, the error would plummet to a very low number here. Okay. So at this point, when we feed forward 0.05 and 0.1, the two output neurons would generate this very close to the target and this also very close to the target. And that is exactly what we want to achieve when we optimize or train our network. So in this example, gradient descent works very well for us. Okay. So how do we